Section 16.2. What we're going to focus on now is dissociation constants. So what we've been working on is Kc. What we're going to focus on is Ka, and Ka is the equilibrium constant in acids. And then we'll work on Kb, which is the equilibrium constant in bases. So in general here, I have HA, an acid. It reacts with water, H2O, and it forms negative A and H3O. Remember, we exclude liquids. So my equilibrium constant or equation is going to be this, H3O over HA times, H3O times A minus over HA. We call the equilibrium constant when we're talking about acids Ka, so this is our equation for Ka, which stays the same. Here's a wide variety of Ka constants. The higher the Ka constant, the stronger the acid. So you can see that phenol at the bottom of this list is a pretty weak acid with a Ka of 1.3 times 10 to the negative 10. Or hydrofluoric or nitrous are a little stronger acids as they're in the 10 to the negative 4th range with their Ka values. So let's do an equation where we can calculate Ka given a particular type of equation. So the pH of a 0.1 molar solution of formic acid, HCOOH, is 2.38. Calculate the Ka for formic acid at this temperature. Well, we know a couple things. We know that that is our equilibrium equation for an acid. That is our Ka equation. Next, we know that the concentration of the formic acid, the HCOH, is 0.1. So we need to figure out the concentration of the other two things. We need to figure out H3O and the HCOOH. Since H3O is our newly formed conjugate acid, we can figure out our base as well off of that. They're going to be in equal amounts. So if we go back to this equation here, well, I don't have the equation yet. H3O and COH are going to be the same concentration from the pH. So if we go ahead and solve for that, if we go ahead and solve for pH, we're going to set this up. pH is equal to the negative log of H3O. We're going to plug in chug. We're going to plug in our numbers. And we're going to solve that the concentration of H3O, and therefore the concentration of HCOO minus is 4.2 times 10 to the negative 3. Now we're going to have an ice table here. With Ka, we just solve for our final concentrations, or our at equilibrium concentrations. We know that we gained 0.423. We know that we gained 4.2 times 10 to the negative 3. And we know that's what we lost. That's what we also lost from our initial concentration. Now, everything, this is what's key here, guys. Everything is a 1-to-1-to-1 ratio, so we don't have to worry about dividing anything by 2 like we have in the past. So it's a 1-to-1-to-1. We figured out the change for each of those. Now, at equilibrium, 0.1 minus that, the change is so small that we can neglect it and we can just keep the concentration as its initial concentration. So we have our equilibriums, which is our changes. We also have the equilibrium for our acid. And since it's so small, we can neglect the change. We're going to take those three concentrations. We're going to plug them into Ka, and we're going to get Ka is 1.8 times 10 to the negative 4th. All right. Something that we're going to work on also when we talk about acids is calculating the percent of ionization. Remember, strong acids ionize completely. Weak acids do not. They only partially dissociate. So we really want to focus on figuring out at what percent do they actually ionize. Well, how we're going to do that is you're going to take the concentration of hydronium divided by the initial concentration of the acid and multiply by 100. So in this example, all right, it tells us that our H3O concentration was 4.2 times 10 to the negative 3rd. Our initial concentration was 0.1. We're going to divide the two, multiply by 100, and that tells us that the percent ionization in this acid was 4.2%. Now, let's do a problem here. Let's go ahead and solve for a problem where we've been given Ka. We have acetic acid. We have a 0.3 initial concentration of acetic acid. It mixes with water, it gives us hydronium, and the acetate ion C2H3O2. It's asking, what it's going to ask is, it tells us the Ka value. We want to know what the ending concentration is of equilibrium of H3O and the acetate ion is, or what is the pH of this solution. Well, how we can do that is this. We know Ka. We know the starting point of acetic acids, 0.3. What we can do is we can do an ice chart where we have change in initial and equilibrium. Our change is minus X. For our initial concentrations, for our products, it's going to be plus X. Remember, the change is so small that we can neglect it, and we can have 0.3. We're assuming that X is very small, so we're going to neglect it, and at equilibrium, our concentration is 0.3, our change is X, our change is X. Now we can plug in X into our equation and solve for X, and X is going to give us the concentration of H3O. So X is equal to 2.3 times 10 to the negative 3. That is equal to X. Now that we've solved that, we can plug that in and solve for the pH. And the pH of this acetic acid solution is 2.64. Last thing that we need to talk about is polyprotic acids. Remember, polyprotic means what? Many. So if we have acids that can give up more than one H, we're going to have multiple Ka values. We'll have Ka1, Ka2, Ka3. For example here, let's look at ascorbic acid. It's H2C6H6O6. We're going to just focus on the two H's. It can give these two H's up. It gives them up one at a time. So if it gives it up, our Ka value for the first H is 8.0 times 10 to the negative 3. Our Ka2 value is when it gives up its second H. If we take an acid like phosphoric acid, halfway down here, H3PO4, it can lose 3 hydrogens, and it's going to lose them one at a time. When it loses them one at a time, we're going to have 3 different Ka values, Ka1, Ka2, and Ka3. Same thing for, sulfuric, H2SO4. We have Ka1 and Ka2. The polyprotic acids are going to, when they break apart, they're going to give their H's away one at a time. So just to kind of review that, when polyprotic acids can have multiple Ka values because they're going to give away their Kas one at a time. So that concludes section 16.2. If you have questions, come in and talk to me because it is very math-based. I kind of ran through the examples. We'll take a little more detailed look at the examples in class tomorrow. Thanks.